Hello, everyone. Mr. Minnick is my name. Math is my game. Today, you can see the date. It's May 17th. It's the day that the Cavs are going to not make it to the it's part day one of that the Cavs aren't going to win the championships. Sorry, I'm trying to anti-jinx the Cavs. I really would like to see them win, but if I say they're going to win, they're going to lose. So I'm anti-jinxing them. Anyway. Um, Here we are. It's second period. I'm joined by my best Algebra II class ever. They're pretty pumped about Chapter 7, Section 3. The title is Logarithmic Functions. Logarithmic Functions as Inverses. That's the book's title. And actually, they left some words out of the title, just because it would be a mile long if they didn't. So 7.3, logarithmic functions as inverses. I'm going to start off with a graph, okay? Normally I would use my interactive graph, but I think the way my computer's been behaving this week, I don't think it'll work so well. So we'll start off with this graph right here. I'm going to graph this function y equals 3 to the power x, okay? From last week, you should recall that the a value here is 1, so the graph goes to the point 0, 1. If you were to picture randomly picking values of x, and we plugged in a 1, 3 to the first power is 3, so the graph would go through the point 1, 3. If we picked another value of x, like 2, 3 to the second power would be 9, so the graph goes to the point 2, 9. And if we went one more time, if we picked a negative 1, I really hope that we get that that's not a negative number. That's going to be a fraction. It's going to be a third, right? So the graph would go through the point negative 1, comma 1 third. Right? So if we sketched that graph, the sketch of the graph is going to be an ascending function. I kind of had a little bobble there. That's why I like to use the crayon. But the graph is going to look like that. Right? If we looked at its domain, the domain of that graph, all the values of x, I think everybody's good with the domain. It goes to the left forever, so it goes to negative infinity. It goes to the right forever, although it gets really high before it goes really far to the right. But so then the domain is all real numbers, right? The range, this is where some of you on the quiz on yesterday kind of dropped the ball for a minute. The graph goes clear up to infinity, right? But what's the lowest that the graph goes? 0. Now, do we use a bracket 0 or parenthesis 0? Parenthesis 0, right on. Good. Awesome. Okay. So what I'm about to do next is kind of like a recap of what we did last week and or the week before. Probably more so the week before. Oh, you know what that is? That's the line defined by y equals x, right? And so what I'm about to do is graph something reflected over that. So rather than plotting the point negative 1 a third, I'm going to graph the point 1 third negative 1. So that's the point 1 third negative 1. Rather than graphing or plotting the point 0, 1, I'm going to plot the point 1, 0. 1, 0. And then that point 1, 3, I'm going to reflect it, so that's going to be the point 3, 1. 3, 1. And finally, the point 2, 9, I'm going to go ahead and reflect it, so I'm going to graph the point 9, 2. 9, 2. So when I sketch this graph, it's going to do this. It's going to do that, okay? And the domain of that graph should be the same as the range of the other one. And it is. It's from 0 to infinity. And then the range of that graph should be the same as the domain of the green one. And it is negative infinity to positive infinity. Now, if I wanted to give that graph a name-o, like B-I-N-G-O, 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 and bingo was his name-o. There was a farmer who had a dog. And Bingo was his name. Oh, I like the clap part. That's the best. Yeah. So what should I call this? Can I safely call it y? Y inverse. I got to call a y inverse. Y inverse is going to equal. Now there is some kind of function that exists in the world that would look like that red one. Anybody know what kind of function it is? A logarithmic function, and that's why the title is what it is. Do you see where the title of today's lesson comes from? So what could the other half of the other part of the title of today's lesson be called? Logarithmic functions as inverses of so the question is, would it be -3 or -x? We're going to fill in the rest of this here in a minute. But let's try to figure out this. It's going to be logarithmic functions as inverses of what? Exponential functions. Right on. As inverses of exponential functions. Okay. As inverses of exponential functions. So in chapter 6 we studied inverse functions, and in chapter 7 we're studying exponential and logarithms, and those two functions are inverses of one another. Now the question is, what's this y inverse equal? It equals some kind of log. We write log instead of logarithm, just to abbreviate. Don't functions usually have an x in them somewhere? Well, this one's going to be the same. We're going to have an x in it, and the x is going to go right there. But we need to put a 3 in there somewhere, and it's not going to be a -3. It's going to be a +3. So I heard somebody say put it at the bottom of it. Somebody in first period said let's put it as an exponent on log. Well, we're actually not going to, it's an inverse, so we're not going to write it as an exponent on the log. We're going to write it, think in terms of a word processor. What's the opposite of a exponent in word processing? If you think about a word processor, you have some number, right? And when you make an exponent, you write a little number beside it and up here. And that number up there is called some kind of script. Up top, it's called a superscript, and when we write it down here, it's called a subscript, right? So what we're going to do is we're going to do this, the subscript. We're going to put that 3 in as a subscript down there. Okay. All right. We doing all right so far? Good. So basically, there's 3 big things that you're going to be able to do by the end of today's lesson, and I'll go ahead and bullet point those. You need to be able to convert. So I can just, actually, I could copy that because you're going to do that twice. You're going to be able to convert and convert. So you're going to be able to convert a log expression into exponential form. I'm abbreviating a lot here if you couldn't tell. But we're going to be converting a logarithmic expression into exponential form. Now it says convert again. You could probably figure out what goes next. Convert an exponential form into a log expression. And the last thing that we're going to be doing today involves getting a numeric answer. There's an E word that means get a single answer that's a number. It's an E word. It means do some things to this expression and get one answer that's a number. Not equate. E what? There we go. Evaluate. Evaluate. Okay. We're going to evaluate log expressions. Okay. So that's kind of a roadmap of where we need to be. And before we can do that, we need to know what a logarithm is. And I told you that this is the part of algebra where your folks, your aunts, your uncles, they say, I liked math until Algebra II, until they started talking about logarithms, because I didn't get them. Well, you know why they didn't get them? They didn't apply them. They didn't know the definition that clears it all up. There's a definition that's going to clear it all up, and there's a definition that's going to confound you. What's that word confound mean? Confuse or make not real clear. So here's the confounding definition, the definition that's not crystal clear. I'll give you the crystal clear definition as well. Don't worry about that. The log base b of some number y is equal to x if y is equal to b to the x. That is the textbook definition of a logarithm. And I'm seeing some people make some weird faces as if I'm a horrible speller, which sometimes I misspell words. Sometimes I misuse words on purpose, like irregardless. If and only if. It means if y equals b to the x, then the log base b of y equals x. And it also means if the log base b of y equals x, then y equals b to the x. So what we've got going on here is two different forms. On the left, I wanted to use my green box here. Here we go. On the left, what we've got going on there is log form. Okay? That's logarithmic form. That's some expression written as a logarithm. And what we can do is we can take that same expression and write it as an exponential form. This is exponential form. And again, that's one of the tasks, that's two of the tasks that you're going to be doing in tonight's exercises and when you go to solve log equations. So we want that other definition, don't we? Because this doesn't make any sense yet. Do you mind if I use curvis? Curvis? I'm going to use my calligraphy pen and I'm going to use curvis. Here we go. A logarithm. I better use cursive all the way through. A logarithm. A logarithm. A logarithm is the power. I could stop right there. I should stop right there because that's all a log is. Now let's think about the word power. There's a long E word that is synonymous with power in math. The superscript. A log is a exponent. That's it. A logarithm is an exponent. You want to know what a logarithm is? It's an exponent. Stop. That's it. We're done. No. There's more to this definition that's going to clear things up. Okay? So a logarithm is the power to which, well, I can write which better than that. To which the base is raised, to which the base is raised. So a log is the power to which the base is raised in order to obtain or get or equal, in order to get, obtain, or equal the number whose log, the number, that's a lot of hoops. The number whose log is being taken, it's weird for a number to possess something, whose log is being taken, is being taken. Okay. Yeah, the number. There was a lot of little humps in that cursive word. So I took a class on taking notes. And you know what they told me? Don't use a highlighter. You know why? Think about it. You're reading a passage of a book, and it's 2.5 pages, and it's important. So what are you going to do? Highlight the whole thing, right? Isn't that usually what happens when we highlight? We end up highlighting like everything. Yeah. So I am going to try to use a highlighter in a crafty fashion here. So a logarithm. This word log right here, that's a logarithm. Now in math class, The word is means some kind of operation or means some kind of numeric or mathematical symbol or equality or inequality. What's it mean? Equals. A logarithm equals. So log equals. It is equal to what? To some power. It's equal to some power. Some power. That power. That power. That's what a log is. Notice on the left side, the log base b of y equals x. The log is equal to a power. What power? The power is x. So it's the power to which the base. What's our base in terms of the characters we've used? What is our base? Our base is b. Good. So I'm running out of highlighters here. Let me see if I can use this box here. So b is my base. So the base is b. The power to which we raise the base is b. In order to get the number whose log is being taken, well, what's that number? Whose number's log is being taken? What are we taking the log of? We're taking the log of, let me get a nice colored crayon that's going to show up blue. The number whose log is being taken. The number whose log is being taken. So if we look at the left side of the expression, we're taking the log of something. What are we taking the log of? We're taking the log of y, right? Well, what we're trying to find, it depends on the context of the problem. Let me just kind of throw this out here. The log base b of y equals x. Okay, that's that. I need this to be this. Okay, that should be good. Log base b of y equals x if what? If y equals, let me get my equal sign going. If y equals what? B to the power x. So what we're saying is this base here raised to this power here equals the number whose log is being taken. So we're taking the log of y. The log of y equals the power that we raise the base to in order to get the number whose log. Does the relationship kind of make a little bit of sense? We're going to look at two examples. And hopefully this will clear this up greatly. Here we go. Example 1. Write each expression in in log form, in log form. Now, I've got to share with you a story, if you don't mind, about tutoring. And I'd never, ever want to badmouth your 6th grade teachers because they do a great job over there at the middle school and the elementary school. But on the sideboard, I've got an image of a triangle sketch that looks kind of like this. And it's got a figure like that. And there was this 6th grader that I was tutoring from our district, and they had this thing, their paper looked like this. And they were asked to find the volume of that 3-dimensional figure. They were asked to find the volume of that 3-dimensional figure. Somebody saying something? You can't because it's 2 different shapes? Well, you're partially right. You can't, but the reason you can't, the 20 is not going because of the 20. You can't find the actual area? The triangle's not too hard to find? You sure about that? Let's think about something. Let me get out a ruler. Hopefully we have time to, I think we have time to do this. I think we have time to do this. So let's get out a ruler. You know, in math, we use the M word, modeling, because we like to model things sometimes, right? So what I'd like to do is I'd like to model something. So I'm going to come up with a line that's, I'm going to use I'm going to scale it down if that's okay. Is it fair that if I use 2.5 for 5, I could use 5 for 10? Everybody go with that? Okay. So I'm just going to trace along this ruler, and 2.5, 2.5 is going to take the place of the 5, right? Okay. Everybody see what I got going on there? So I'm going to need another one of those. Okay. So each of those segments is 2.5 or 5 units long. And then this other one is going to represent something that's, oh, I need to go a little bit longer if it's 11, don't I? Oh, man. If it's 11, it needs to be a little bit longer than this. So is that okay? Is that good enough? It's a little bit longer than that? Okay. All right. All right. Vote. Oh, come on. Come on. There we go. Okay, got it. So let's see if I can't make a triangle out of this. Can I make a triangle out of that? I'm not changing the length of these. Can I make a triangle out of that? No. The point I'm getting at here is sometimes in math we try to generate examples on the fly. And when we do, we mess up. So what I'm telling you is whenever I make up examples for logarithms, I'm probably going to mess up. And if I do, I want you to call me out on it. Because the expressions that I give you have to mathematically make sense. Okay? If I try to tell you that 6 to the power 4 equals 15, well, I'm wrong. And there's no way we can use that expression in a logarithm expression. So what I'm getting at is all the expressions that I give you, like the one here in example 1a, 6 to the third power, I can't say that that equals 18 because that really doesn't equal 18, does it? What does 6 to the third power equal? Is it the area code in Cleveland? I think it's 216. Okay. Number B, let's go with 1 over 225, the quantity to the negative 1/2 equals 15. And I've kind of written these backwards. I've kind of written these in the inverse order. Do you want? Should I write them forward? Hopefully that doesn't mess you up too bad. So I'm going to rewrite this. 216 equals 6 cubed. And 1 over 225 to the negative first equals 15. 15 equals, oh man, it's going to be a long day today. I could tell it already. 15 equals 1 over 225 to the negative 1/2 power. Okay. Number C, we'll say that that 100 equals 10. 100 equals 10 to what power? 10 to the second. And for number D, we'll say that 20.0855 is approximately equal to e to the third power. That's E as in Euler's number, right on. Okay? So we should be able to put A and B in the right form. Let's go back for a minute. Log form. What do we have in log form? We have the log base something of something equals something, right? Okay. So for our answers here, we should be writing the log base something of something equals something. And in a sense, all we got to do is fill in those 3 boxes with whatever goes in those 3 boxes, right? Now, if you understood exponents, you'll understand what bases are. A base is the thing that's being raised to some power, right? I think the base is the easiest thing to fill in. One thing you might want to make a note of to yourself is self, the base, this thing right here, this thing right here. In a logarithmic expression, the base is it's the subscript, right? In a logarithmic expression, the base is the subscript. In an exponential expression, it's the thing being raised to a power. So let's see. In example 1, number A, what's our subscript going to be? Our base going to be 6. Everybody good with that? Okay. So log base 6, the of something, the number we're taking the log of is really confusing. And I'm not going to fill that in, but I want to go back to the definition of a log. A log is what? A log equals the power. A log is an exponent. That's all you need to know. A log is an exponent. So a log equals the exponent. So this expression is going to equal an exponent. So it equals 3. Do you see why I like to fill those two boxes in first? It's a fail-safe method. The base, the thing raised to a power. The power is what the log expression equals. And so the number whose log is being taken then is the only thing that's left. The 216. So far, so good. Questions? Let's try example 1b. What's our base going to be? Our base is 1 over 225. Awesome. 1 over 225. Forget the number whose log is being taken. The log is the power. The log equals the power. So that log expression is going to equal negative 1/2. And whose number are we taking the log of? We're taking the log of 15. Okay. Questions, comments? So the question is, how would we put this into the calculator? Terrific question. I'm really glad you asked. Let me bring up both calculators and I'll answer that in a minute. Before we can answer C and D, I need to clue you in on something. There are two special kind of logarithms. There are two special logs. One of them has a base of 10. One has a base 10, and it's called the common log. It's called the common log, okay? Its base is 10. It's the common log, and the deal with it is there's no need there is no need to write the base. And when I say base, I mean the subscript. Okay? We don't need to write the subscript. It's assumed that it's 10. It's assumed that it's 10. The cool thing about these is that if you understand scientific notation, these ones are going to be real easy to handle. The kind of ironic thing is the old scientific calculators can handle and evaluate these logarithms for you. If you notice, there's a button right next to 7 on this calculator. Let me see if I can make it a little bigger. Do you see the button right next to 7, what it says? It says log. That means the log base 10. Okay, that means the log base 10. Shrink this back down. So if we wanted to evaluate a logarithm on this calculator, it will evaluate them if the base is 10. And we'll come back to evaluating them. The other one is if the base is E. And what this is called is the natural log. Kind of weird names: common log, natural log. So when we write this, we don't even write the word log. We don't write L-O-G. We do not write the word L-O-G. So you're probably saying, well, what do we write? Well, look on the calculator. There's an L-O-G button, right? There's another button right next to L-O-G that represents the common log. Do you see it? ln. Okay? This one we use ln. ln. What's ln stand for? Maybe French people came up with it. The log natural. The natural log. Okay? So what I'm saying is ln could kind of be perceived as, you could kind of think of this as the same thing as the log, even though we don't write log. You could say that this is the same thing as the log base e. Does that make sense? In the log log, we could think of this as the log, oh, I did it again. The log log is the same thing as the log log base 10. Okay. All right. So that'll help us with number C. So number C, what are we going to write? The log. Now what's the base? The base is 10. Do we need to write it? No, the base is 10. The base is 10, but we don't need to write it. So it's of something and it equals something. It's equal to 2, and we're taking the log of 100. How's everybody feel about that one? Good? Okay. The base is 10, yeah. So again, one more time, the base down here is 10. Remember what a log is saying. Where's my magic? That's just for the 10, right? What we're saying is this number to this power should equal that. The base to that power should equal that. Question? I would not mark it off if you wrote the 10. I might make a note that you don't need to write it, but I wouldn't mark it wrong. Good question. Let's see if we got number D figured out. Yeah. It wouldn't be log. ln. ln of what? Well, the ln's going to be approximately equal 3. We're not even going to write the word e. The ln is approximately 3, but what are we taking the log of? 20.0855. The log's base is already e. Remember, when we write ln, it's as if we wrote the log. It's as if we wrote the log base e. Last week on the worksheet, we had a thing. Does anybody remember what e to the power 3 is? It's about 20.085. Remember that? Okay. 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 Let's go the other way with this. Example 2. Here we go. Example 2. Write each expression in exponential form. These are a lot easier. A lot easier. A, B, C, D, and E. Let's have the log of 0.1 equals -1. Let's have the ln of e to the smiley face equals smiley face. It's kind of confusing. You'll see. Let's go with the log base 2 of 16 equals 4. Let's go with the log base 289 of 17 equals 1/2. And let's go with the log base 27 of 3 equals 1/3. Okay. So here we always start with the number whose log is being taken. So in example 2a, whose number's log is being taken? 0.1. So we're going to have 0.1 equals the base. What's our base? It's not there. Oh. 10 to the power. A log is a power. The power equals what the log equals. The log equals -1, so the power is -1. Make sense? Okay, let's hit the next one. Well, let's skip the next one. The next one's really confusing. Let's go to number C. 16 equals 2 to the 4th. There it is. One thing I should note, because I know somebody's thinking of it, should we write 2 to the 4th equals 16 or 16 equals 2 to the 4th, or doesn't it really matter? It doesn't matter because of the reflexive property. Okay. Number D here, what do we have? 17 equals 289 to the 1/2. Good. Remember, raising something to the 1/2 is like taking its no, not its reciprocal, it's square root. Okay. Number E, what do we think about E? 3 equals 27 to the 1/3. So we're saying 27's third root is 3. Does that make sense? Yes. And these have to make sense. Otherwise, we got that crazy triangle that your 6th grade teacher gave you, and that's not even possible. Number B, I kind of skipped over that one. It's tricky. Remember, it's like we have the log base E. So isn't it smiley face equals smiley face? Well, we start with whatever we're taking the log of, and we're taking the log of e to the smiley face, right? So this one's going to be e to the smiley face. To be clear, this e to the smiley face is the same as the other one highlighted. The number whose log is being taken is equal to the base. What's our base? Is equal to the base, so it's equal to e to what power? A log is a power. A log is a power. So this smiley face here is the same as the smiley face that we raised that base to. Does that expression make sense? E to the smiley face equals e to the smiley face? Yeah, and it should. And the e's are so easy, no pun intended, that you're going to get confused with them. When you take pre-calculus and calculus, you're either going to love e's and ln's or you're going to hate them. They're so easy that you overthink them. Okay. Any questions about any of those? We only have one more idea left to talk about. Here it is. Example 3, evaluate. So we had a question about evaluating in the calculator. After we evaluate these by hand, I'll gladly show you that on the calculator. So we're going to evaluate each of these log expressions, such as the log base 2 of 1,024, such as the log base yeah, I can't even think today. The log base, I'm drawing a blank here. The log base 200 of 10 radical 2. Ooh. How are we going to do that one? Such as the ln of e to the 6th, such as the log log of 1,000,000, such as the log base 8 of 1/2. Wow. So sometimes you need to be able to talk to yourself to be good at math. If I'm looking at example 3a, what I'm really asking myself is this. Self, is there some power that I can raise 2 to in order for that to equal 1,024? Because that's really the question I'm answering. What power can I raise 2 to equal 1,024? To the 10th. Nice. Nice. The answer is 10. When we evaluate, remember what we're doing. We're getting a one-number answer. So the answer here is 10 because we're raising 2 to the 10th power to get 1,024. The answer is just 10. But the question that you're asking yourself is, what power do I raise 2 to get 1,024? And some people, they like to set up an equation like this. They like to say, okay, so this log base 2 of 1,024 equals question mark. And then they'll write this expression. Question. So we got a couple more to do, and we'll do that in a second. Anybody think they have number B figured out? Let's skip B for a minute. B's tough. Anybody think they have number C figured out? Number C, we're asking ourselves, what power do we raise the base to? What is our base? Our base is E. We're asking ourselves, what power do we raise E to to equal the number whose log is being taken. Well, whose number's log is being taken? Whose number's log is being taken? Oh, come on. E to the sixth is the number whose log is being taken. So what power do we raise e to get e to the sixth? 6. What did I tell you about the ones with e's? You're either going to love them or hate them. They're either really easy or you're going to overthink them. Number D, what power do I raise the base to get a million? What is the base? 10. What power do I raise 10 to get a million? Ten to the third. Think of your scientific notation. 1 times 10 to the third is 1,000. 1 times 10 to the fourth is 10,000. It's going to be 6. Right? Number E is kind of tricky. Number E is kind of tricky. What power do I raise 8 to get a half? Wouldn't I need to flip it? So that's going to be a negative power, right? I would need to flip it. So that's going to be some kind of negative power. What power do I raise 8 to get 2? Do I want to take its third root? This one will be negative 1/3. Okay, that one's tricky. Number B, that one's tricky. Anybody think they figured out B? What power do I raise 200 to get 10 rad 2? It's like taking its square root, right? The square root of 200 is 10 rad 2. So what power would that be raising it to? To the 1/2. TI Inspire, you're going to love the TI Inspire. This is why you're going to love it. Check this out. The TI Inspire, when you press the log button, it's Control 10 to the X. Look what it gives you. Oh, snap. It gives you the provision for the base, doesn't it? Ha! Got him. It's been real. It's been fun. I hope it's been real fun. I'll see you all next time. Shout out to the future Mr. Minnick. Shout out to my second period class. Shout out to anybody watching back at home. See you.